Hello, everyone. Welcome to the Just Infrastructure's Fall 2021 Speaker Series. Today is the season finale of our talk series for Fall 2021. My name is Inde Gupta, and along with Carrie Karaholios and Anita Chan, my fellow co-leads of the Just Infrastructures Initiative, we welcome you to today's event.
For those of you who don't know us yet, Just Infrastructures is an initiative created by researchers to interrogate the complex interactions between people, algorithms, and AI-driven systems. You can learn more about us on our website at just-infras.illinois.edu. A link has been added to the chat. You can see recordings of all 7 talks from spring 2021 and the 5 talks from fall 2021 at this website.
We'd like to thank those who fund and support us: the Computer Science Department at the University of Illinois, the School of Information Sciences, the Granger College of Engineering's SRI program, Capital One, and the Community Data Clinic. We have a long list of non-financial co-sponsors you can see on our website, and we would like to thank them as well. We're also simulcasting in the Siebel Center for Design, the iSchool's Room 126, and the CS8CI Lab. Thank you for those meeting space accommodations.
To ask a question, please use the Q&A box in the bottom of your Zoom interface. For our live audiences in the Siebel Center for Design, the iSchool, and the CS building, feel free to use a question strip and return that to the room host. We'll go through the questions at the end of the talk. Please feel free to indicate what unit, department, organization you are from when you submit your question. Closed captioning support is also available, and you can request any tech support. The talk is being recorded, and we're live tweeting this talk with the hashtag #JustInfrastructures.
I'd like to now ask you to join me in a land acknowledgement. As a land grant institution, the University of Illinois at Urbana-Champaign has a responsibility to acknowledge the historical context in which it exists and the exclusions and erasures of the indigenous peoples on whose lands it is located.
We are currently on the lands of several nations, including Peoria, Kaskaskia, Waukesha, Miami, Muscatine, Ottawa, Sauk, Meskwaki, Kickapoo, Potawatomi, Ojibwe, and Chickasaw nations. This acknowledgement demonstrates a commitment to the process of working to dismantle the ongoing legacies of settler colonialism. Acknowledgements invite us to ask, what does it mean to live in a post-neo-colonial world? What did it take for us to get here? And how can we be accountable for our part in history?
We'd now like to turn it over to our esteemed presenter. We are extremely honored to have Mahadev Satyanarayanan with us here today. He goes by Satya. Satya's multi-decade research career has focused on the challenges of performance, scalability, availability, and trust in information systems that reach from the cloud to the mobile edge of the internet. In the course of this work, he has pioneered many advances in distributed systems, mobile computing, pervasive computing, and the Internet of Things, also known as IoT. Satya is often called the father of edge computing, as his seminal 2009 publication, The Case for VM-based Cloudless and Mobile Computing, led to the birth of the entire area of edge computing in industry and academia. Satya is the Carnegie Group University Professor of Computer Science at Carnegie Mellon University. He received his PhD also from Carnegie Mellon and bachelor's and master's degrees from the Indian Institute of Technology, Madras in India. He's a fellow of the ACM and a fellow of the IEEE. I'm really delighted to have Satya joining us here today, and I can't wait to hear his insights and his latest work. On behalf of my co-organizers, our organizing team, and all our listeners out there in the Zoom and YouTube ethers, I extend a warm welcome to Satya. Welcome, Satya, and the floor is yours.
Thank you very much for that warm introduction, Indy. Can you hear me clearly? Perfect. So to all our guests who are listening in, I can't see you, but hopefully what I have to say to you will be interesting and hopefully will stimulate thought and introspection on the many ideas that underlie what I'm going to talk to you about in the next 45 minutes or so. So as the title of the talk says, it is really in 3 parts. The unifying thread is a concept called wearable cognitive assistance, and I'm going to tell you about it today. But I'd like to structure it as, how did it come about, the vision? Then the reality, what actually works, working code trumps all hype is my motto. and then about the challenges. Where do we go from here? And so join me on this journey as we go on it. So by coincidence, each of these three parts of the talk span roughly a decade. So the first part of it, the vision part of it, is just over a decade, starting in 1991. Many of you are familiar with Mark Weiser, who unfortunately passed away quite young. But he's best known for a paper that he wrote and published in Scientific American in 1991, September 1991. It's very important to understand that the Mosaic browser had not yet been released to the world from Illinois in 1991. So we knew about the internet and networking, but certainly not about the web and all the things that we take for granted today. So the vision that Mark Weiser described in this paper was called appropriately the computer for the 21st century. So this is perfect as a lead-in to this talk. What makes this paper so well known and so widely cited is the key insight that he expresses in the first few sentences of the introduction. That is, the most profound technologies are ones that we aren't even aware of. They disappear. And they become so much a part of the fabric of our lives that we stop thinking about them consciously. So this was a very, very profound idea. And the rest of the paper went on to show if you could create environments where sensing and compute and communication were plentiful, but somehow gracefully integrated with the humans, then you could achieve this goal. And the paper gave some examples, and it was an inspiring paper. It led to a decade of work at Xerox PARC. It inspired a vision that Mark Weiser called ubiquitous computing. That was the name that was used for about a decade. Some people continue to use it. Sometime in the late 1990s, IBM embraced this vision under the name pervasive computing. That was the name that it had for about another 10, 15 years. In fact, in 2002, I was the founding editor-in-chief of a publication called IEEE Pervasive Computing, which continues to be a publication dedicated to these ideas and their successors. And by about 2015, maybe a few years earlier, industry had caught on, and they embraced it using the name Internet of Things. Now, it's actually a bad name. And the reason is because, in contrast to Mark Weiser, who placed the human and the disappearance of technologies at the centerpiece of the whole vision, Internet of Things focuses on things rather than people. But be that as it may, that's the title we are stuck with. And so regardless of which title you use, this is the domain in which all my remarks over the next 40 or so minutes this is the context in which it'll apply. So I mentioned I was the founding editor-in-chief of this publication, IEEE Pervasive Computing, and every issue I got the opportunity to write a 2-page message from the editor-in-chief. So I could do with it what I wanted. And I used it often to share my thoughts with the readership on a number of interesting futuristic thoughts. And one of them in 2004 was called Augmenting Cognition. And the roots of what I'm describing to you today are really described in that thought piece. So you can find this on the web. Basically, as you see in the text on the right side of the slide, which is a quote from the thought piece, it imagines a wearable computer with some form of display and eyeglasses and connected to a camera, which senses the world and basically improves your cognition through some form of augmented reality. And, you know, it was mostly science fiction-ish, but at the end of the paper, I did say it's difficult to predict when systems of this kind will become reality. They don't exist even as lab prototypes, but fortunately, compelling visions of the future have a habit of becoming true sooner than most people think possible. And that turned out, fortunately, to be a very prophetic comment. Fast forward now another decade. So we're now at roughly 2014, 2015, and in collaboration with 3 other colleagues at Carnegie Mellon University, Marshall Ebert, who's an expert in computer vision, Dan Zworyk, who was one of the creators of the world's earliest wearable computers, and Bobby Klatsky, who is a world expert in cognitive psychology and learning, cognitive learning. We were successful in winning a large NSF grant by the name Wearable Cognitive Assistant. So it just ended 3 months ago. So in reality, what I'm sharing with you is a distillation of what we learned from the time period of trying to make this vision come true, okay? So by the way, there are a lot of publications. I've just given a few highlights, 5 of these here. And I'm obviously going to go very superficially into many topics in this short talk. You can find a lot more details in these papers, which are all available through the usual means. Whoops. So here's what wearable cognitive assistance is about. Imagine this user on the left here. She happens to be wearing a mobile device. It is Google Glass in this case, but could be any other head-mounted device. Inside it are both a camera, a microphone, accelerometers, gyroscope, you name the sensors, you can probably find them on that device. Over low latency, high bandwidth communication, these sensor values, frames, sound segments, etc., are transmitted to a nearby edge computing node, a very powerful one with GPU accelerators, etc. We call this a cloudlet because it's a small cloud just close by instead of being far away. And running on that cloudlet in real time, the data is processed in a variety of ways. And exactly how it's processed is application specific. So in many cases, it might involve computer vision and scene analysis. It could involve language, speech recognition and natural language recognition. It could involve things like recognizing who is in front of you, et cetera, et cetera. So precisely the nature of the computation is quite open-ended, but the important point is that this is a closed loop system. The result of the real-time processing is sent back to the user faster than she can think. And so hopefully what she gets back as guidance is helpful in some way to whatever she is trying to do. So in metaphor that is very useful is an angel on your shoulder that whispers helpful guidance and helps you succeed in whatever you're trying to do. So we call this Gabriel because Gabriel is an angel. And this metaphor relies critically on low latency because at the heart of this whole metaphor is the fact that our goal is not just to match human cognition, it's actually to improve upon it. So if you're going to try and improve upon human cognition, which is amazingly accurate and amazingly fast, you have an extraordinarily short time budget to work with it. And so here are some numbers. These are all published values that have been obtained from the literature. Face recognition. Humans can recognize familiar faces on the order of about 350 to 400 milliseconds. And amazingly, the human cognitive system is sensitive enough that if what your eyes are telling you differ from what your balance organs in your inner ear are telling you, if the difference is more than 16 milliseconds, then for many people, it results in nausea, a sensation similar to seasickness. So this is why head tracking in virtual reality and augmented reality has to be very, very tight in order to meet these bounds. So we could go on, but you get the point that not only are humans amazingly accurate, every day we recognize hundreds, maybe even thousands of faces without making an error. And the few times we make an error, it's actually memorable because we remember it. So I hope I've convinced you that from a computer science point of view, this is an enormously challenging technical problem. But a fair question to ask is, how exactly would this help people? Why should we bother doing this? So let me walk you through a trivial example, but it makes the point. Imagine this person who's shown here using a wearable device for cooking. Now, interestingly, one of the earliest Google Glass apps was a recipe app. It would show you on your little display exactly what I'm showing on the screen here. It says heat 1 tablespoon oil in a large skillet until the oil sizzles. And the nice thing about a wearable device is, of course, your hands are free. He can do his chopping. He can glance up at the instruction, and then he can say next, and it shows the next step. Very nice. People used it. This was deployed by about 2013, 14. But notice what it is missing. If a good friend of this person was standing next to him, giving guidance, she might say, wait, the oil is not sizzling. Don't put the stuff in yet. You're going to make a mess. That is the critical difference. It is sensing the real world, extracting task-relevant information, and then acting on it fast enough to give useful guidance to the user. And if you can do this, both accurately enough and fast enough, then you have transformed the capabilities of the average human being. Now, this sounds a little esoteric, but every single one of you listening to this talk has used a system like this. This is what GPS navigation is like. Those of us who have gray hair remember a time when it didn't exist. We had to use paper maps. Today, you rely on GPS navigation. It gives you a step-by-step guidance. You follow it. If you fail to listen to the instruction, for example, it says take the next exit and you don't, it recognizes this by itself very quickly and then tells you how to recover. What is the corrective action you should perform? And so we use this every day. Probably 1 billion people in the world use it, and it has transformed our lives. Could we generalize this metaphor? Could we do this for other complicated tasks like repairing my bicycle or performing some medical procedure in a remote part of the world where there is no one more experienced or skilled than you, and even though you have never done this before, you're the best person around to try and do it? Could you generalize this metaphor in this way? And so this is the right way to think about it. We have created an open source platform called Gabriel, and I won't go through the details of this implementation. It's in one of the published papers and it's online in our website. You can get it from GitHub. But the basic idea is it provides the flow control and the opportunity to have plugins which perform the kind of task-specific real-time processing needed to accomplish the goals that I just described. The rest of the talk is really all about how do we create applications that leverage the infrastructure and leverage a platform like this and actually do useful things. So I'm going to share with you a short video of the very first cognitive assistant that we ever built. This was built at the end of 2014, and we picked the simplest task that we knew, which was building a Lego kit, making a simple task. I'm going to show you just a few seconds of video, and then I'll give you some details that are relevant to how it works.
Once the task is loaded, our system will provide both visual and verbal guidance to the next step.
Welcome to the Lego task. As a first step, please find a piece of 1x4 green brick and put it on the board.
So what you're seeing is the first person view.
Now find a 1x1 white piece and add it to the top of the current model.
The little display shows what the user is seeing in the Google Glass display.
Good job. Now find a 1x1 black piece and add it to the top right of the current model.
And of course, the voice is what the user hears, just like your GPS navigation.
Great. Now find a 1x2 white piece and add it to the top of the current model.
Notice that it doesn't give the next instruction until it sees that you've completed the previous one.
Now find a 1x1 green piece and add it to the top left of the current model.
And the true test is, of course, whether it
Once
can
you get
catch
something
errors.
wrong, our system will tell you how to fix it.
You are quite close. Now slightly move the 1x1 green piece to the right by 1 brick size. Great. Now find a 1x1 green piece and add it to the top left of the.
Okay, so you get the idea, right? That this is how the system works from a user experience point of view. Here's what's happening on each video frame. All that you need to know to understand the state of this application is the matrix at the bottom, step J on the very last row, where the numbers tell you what color of Lego brick is in that spot. So 0 means nothing, 1 means white, there's some encoding. If you notice the total encoding, that trivial little matrix, maybe 100 bytes is what it'll take of storage. But you have to extract those crucial 100 bytes from an input image, which is shown in the very first top corner, top left corner, which might be a 15 megapixel image. So this is what every single task involves. We think of the task relevant distilled information as a symbolic representation of the current progress of the task. You can think of it like a program counter, except in a task specific way. And the input image you can think of as the analog world. It's not really analog, it's digital, but the state space is so large that it's almost analog. So what is happening in real time is an analog to digital conversion that is task specific. And you have to do this accurately and fast in order to build these class of applications. Now, the Lego task didn't seem especially latency sensitive. Who cares if the response came back a little slower? The user might be a little frustrated, but big deal. Here's an example where it is obvious why latency matters.
Our Google Glass-based ping pong assistant helps the user to play better ping pong by whispering whether the user should hit to the left or to the right. The hint is based on the observed ball position and opponent position.
Left. Left.
Okay, so what is going on here is a cognitive assistant that has to provide guidance fast enough for the human motor action to be able to hit the ball in time to actually win the rally. So this is an example of one where obviously a slow response would be worthless because in fact it would be too late to act upon the information. Now, these two examples were clearly toys, but let me show you one where it's clear that this is starting to be useful. This is an experience that perhaps every one of you on this call has had, which is buying a kit of some kind, perhaps from Ikea, and then putting it together. Today, you have to follow the instructions on a sheet of paper. They're not very well done, not sometimes, and it's hard and confusing. How nice it would be.
In this application, our wearable system helps the user to assemble a piece of furniture. We are demonstrating using a real Ikea lamp. But instead of reading the instruction sheet, the user gets instructions from short video clips displayed on a smart glass. And our system provides appropriate feedback based on real-time analysis of user action.
Put the base on the table.
Notice now, in this case, the display shows a small video that tells you what to do. And until you have done something that
Screw the
matches,
pipe on top of the base.
it is quiet.
Job. Now find the shade cover and expand it.
And once again, the true test is, can you detect errors?
Put the iron wires to support the shade and show the top view of the shade.
As we can see, the system is able to accurately and quickly recognize a user's progress and provide appropriate video tutorial. The video tutorial will play repeatedly until the user finishes a step. When the user makes a mistake, the system will quickly catch it and offer instructions to fix it.
You have attached one wire. Now find another one to support the shade.
So it notices the fact that he forgot to attach the second wire. That's quite a subtle error. The computer vision you need to detect that little missing piece is actually non-trivial, but it's possible and doable, as this demo shows.
Now unscrew the black ring out of the pipe.
So you get the picture here. So we have shown, and over the course of the past 6 years, 7 years, we've built almost 20, in fact, over 20 examples of increasing complexity. What I've shown you are some of the earlier ones. The more recent ones are even more complex. So obviously, this is very interesting. It's very promising. As proofs of concept of the idea of wearable cognitive assistance, I think most of you will agree that this is pretty compelling evidence that there is merit to this concept. So where might this actually prove to be useful? Clearly, assembly of any kind. We've just shown the IKEA assembly, but many other tasks. Either it could be a homeowner, end user, or possibly helping a worker in a factory with short runs of products to put together something that is done infrequently, because the last time this person did something like this was maybe quite a while ago. So it's in contrast to a classic factory setting where millions of units of some widget are produced before there's a change. Here, when short-run manufacturing is being done, then the ability to deliver just-in-time guidance becomes extremely valuable. Even more valuable is after a piece of industrial equipment is installed. So here's a person in this picture trying to repair some motor in a factory, perhaps, that has ground to a halt because there's a problem. This person is part of the team that has been sent out to fix it. It's quite possible that this is an old 30-year-old piece of equipment that he has never worked on before. Getting the guidance for that precise item, even though he's a generally skilled workman, can make a big difference in terms of success and how long it takes. Here's a number that is really very interesting. It is estimated that when a typical jetliner say a Boeing 737, loaded with passengers and ready to depart from the jetway, is held up because of some mechanical defect, perhaps with the jetway or some other mechanical defect, the average cost to the airline is about $600 per minute. So a 20-minute delay is a substantial expense, a hit on the bottom line of the aircraft. And it might take that long or longer for the mechanic who knows that particular equipment to come from the far end of the airport, which is where he or she is currently located. On the other hand, if a mechanic who's already here could be given the precise guidance to unwedge whatever is wedged, the savings to the bottom line are very clear. So in general, expertise is rare by definition. The ability to deliver expertise just in time, especially in industrial troubleshooting settings, is, I believe, one of the early use cases that will prove economically viable. Another example is medical training. Here's either an intern or more likely a medical student being guided on how to examine a patient by a fully qualified doctor. Notice that he is learning on a mannequin. It's not even a real human being. Why is the expensive doctor needed here? He could receive guidance just in time from a cognitive assistant and learn. And then perhaps the first time he works on a real patient, that might be the time when the doctor is really needed. So if we look at our instructional techniques for many, many professions, there's a good chance that there are examples like this that could benefit enormously from wearable cognitive assistance. Another example, which is also enormously valuable, is in elder care. A good way to let people stay at home as they grow older is to be able to have them use monitoring devices to take their blood pressure, their glucose level, etc. The readings get transmitted directly to the doctor. And so it's a win for everybody. Of course, this doesn't work unless the instrument is used properly. And especially senior citizens, perhaps in the early stages of dementia of various kinds, might not put on the device properly. They may put it down upside down, or the contacts are not proper, etc. Being able to guide in real time and correct a mistake in actually using a medical device is another example of something that could be very valuable. And last but not least, all of us could use help with willpower. Just as you're about to stuff yourself with something unhealthy, imagine a voice yelling in your ear, stop, eat an apple instead. And perhaps it'll make a difference in helping us live better lives. So I hope I've convinced you that this general concept of wearable cognitive assistance is enormous potential. There's a lot of technical information that I'm glossing over here, but let me share one thing with you, which is, where does the time go when we're talking about a few hundred milliseconds, which is the order of magnitude of many of the times I talked about total end-to-end, what is called motion to photon latency of the order of a few hundred milliseconds. Where does it go? So here is a set of measurements from some of the applications we've built. On the extreme left are the shortest latencies. So if you use a cloudlet, which is edge computing based, on the extreme left, the pool application has an end-to-end latency of 70 milliseconds. The same backend code running in the cloud in Amazon or Azure takes about 2.5 or a little over twice as long to execute. So it may make a difference in this particular application, but there's certainly many in which it makes a big difference. If you drill down and look at where the time goes, the green part is the transmission time for the image data, the video data on the uplink. The yellow is the compute, and the blue is the transmission time on the network for the response back to the user to give guidance. So in the example of where an image of the next step is transmitted, that could involve image transmission or video transmission. So you notice here consistently two things. One, when you use edge computing, which is represented by cloudlet, the uplink and downlink times basically drop to very small values. They're certainly much better than running in the cloud. But equally importantly, as you move to the right, the yellow gets bigger and bigger and pretty soon dominates the total end-to-end latency. So it hardly matters whether you're running at the edge or whether you're running at the cloud. In fact, one of the biggest insights, certainly for us, from our early concepts of edge computing, was that to really have edge computing make a big difference, you need much beefier hardware at the edge than we ever thought was needed. It's not just more cores, but also GPUs and possibly ASICs, which are accelerating the processing so that even the yellow portion. So this graph was without a GPU. When you add a GPU, the rightmost picture basically shrinks down to the picture on the left. So you're able to meet very tight tolerances. Most recently, we have been exploring escalation to a human expert. So as we have built these applications, one thing that has become very clear is as the number of states in the task increases, you effectively have an explosion, a combinatorial explosion of many ways in which to do something wrong. The number of ways to do it right is very few, but the number of ways to get it wrong is large and keeps increasing as task complexity increases. The problem is, if I have to write code to handle every case, even the ones that are almost never actually encountered in practice, that's a very, very expensive and in fact self-defeating approach. So an approach that has worked very well, that we're very excited about, is where the cognitive assistant handles the correct paths and possibly common errors, the most frequent errors that people make. But anything outside the scope of what it can cope with gets escalated via Zoom. So we've actually integrated the actual Zoom mechanism into Gabriel to a remote expert. So at the bottom here is an example of a worker receiving just-in-time guidance on something complex. I think it's a jet engine in this case. Most of the time, he's interacting only with the software on a nearby cloudlet. But when he makes a mistake that the software cannot recognize, or explicitly, when he's confused by whatever it's trying to tell him, he can escalate to a remote expert, who of course could be anywhere on the internet. Now, his video and other sensor feeds, the microphone and video feeds, are directly seen by the remote experts, just like you're watching me now. So she can talk to him, guide him back on track, and then set the state of the cognitive assistant to continue processing. So this approach of using human experts as an exception handler is actually a very promising and very successful approach. And I think in the long run, this is going to be the path that is going to be very successful for real world tasks. Now, interestingly, there are products. Microsoft offers a commercial product called 365 Dynamic Remote Assistant for the Microsoft HoloLens. So let's take a look at that website. This is the Microsoft website, and it shows work together from anywhere. Here's a person on the right with HoloLens, and you can see here a person, an expert at the bottom, the woman who's helping this person correctly do something. So here's the difference between such a system and what we are talking about here. In the Microsoft Dynamic Remote Assistant, you need one expert continuously paying attention to one worker. That's not scalable. In using human experts as escalation mechanisms or exception handlers, you can have one expert for maybe 10, 20 workers. Most of the time, the software is taking care of them once in a while, the expert is helping them. So in a sense, it's a little bit like the call centers where you have a first layer of software. The difference is, instead of the software being reverse engineered into an existing model, we are starting out from the software being the primary mode of interaction and the remote human being the exception. So we think that the combination of this approach with many of the ideas I've already shared together have the opportunity to be truly transformative. I want to get now to the last part of my talk, which is looking ahead. So we at this point, the reality part, I think there's no doubt whatsoever that systems of the kind we're talking about can actually be built, they can actually be useful. Can they be commercially successful? Will it deliver real value to real users? Will it be widespread in use in a few years? Those are the unanswered questions. So I'd like to look at those in this last part of my talk. And it's interesting to look back and ask what happened to those 10 years between when I first articulated the augmenting cognition vision and 2015, when we got an actual NSF grant to do the work. That was a long time. What happened during that time? Why was there a delay? Well, a lot had to happen. First of all, it was not until 2012 that the world recognized how valuable deep neural networks could be in terms of computer vision, accuracy in object detection, etc. So that's a key innovation. And ever since then, DNN-based cognitive algorithms have dominated artificial intelligence. So that was an important technology that was foundational. Google Glass, as one of the first widely available commercial products, was released in 2013. Again, exactly in this period. Today, we have many more, but the point is that this was an example of a technology that needed some more years to mature. And last but not least, Indy mentioned edge computing. The need for it as a contrast to cloud computing and the need for low latency, et cetera, were really articulated in 2009. And it took a few more years for industry to realize its significance. So that long period really was needed for all of the foundational technologies behind wearable cognitive assistant to really come together. It was possible to imagine how to do this, but to really do this, you couldn't do it without these foundations. So it is possible.
Satya,
Yes.
just a 5-minute warning as you requested. We have quite a few questions queued up, so thank you.
Perfect. Yeah, 5 minutes is a good time. So this metaphor of needing a little catch-up time is exactly right, and I believe it's what's going to happen with wearable cognitive assistance. I believe that there's going to be a small period of time, hopefully not a whole decade, but maybe 2, 3, 4 years, during which the technology has to move from the lab into the real world. And although nothing much may be visible during that dormant period, a lot has to go on. Specifically, edge computing today is just starting. It is commercially being offered by a number of telcos. It's not yet mainstream, so it's in transition. What is interesting is wearable cognitive assistance would in fact accelerate the adoption of edge computing because it's one of the killer apps for edge computing. So there's a chicken or egg aspect to it. Same point about wearable devices. They exist, you can buy them, but the demand for them primarily comes from augmented reality and a small number of industrial use cases. The killer app, the thing that consumes most of those devices, are the kind of use cases that I'm describing here. So again, a chicken or egg. And the same point could also be made, frankly, for 5G. 5G today is primarily driven by video delivery and the bandwidth that it provides. The lower latency not many applications can actually use it. What I'm describing here is one of those classes of applications. So continued improvements in machine learning-based computer vision, this is happening, that will also help. The one thing that will not happen on its own are the tools to simplify and speed up development of this class of applications. So here is a use case. One of the master's students at the moment, as we speak, is working on creating a cognitive assistant for this Ikea kit. You can go buy this. It's called Rascog. It's 25 parts, $30. You can go get it. Now, he is doing this for course credit. And he gets basically an amount of credit which maps roughly to about 200 person hours of time. That's what, for that class of person, it takes. Now, if you already had an experienced developer, perhaps you could cut this in half, maybe 2/3, because the person may already know the tools kit, has built applications like this before. But contrast it to a high school student who can create her first website, really decent one, in a few hours, right? So what this says is there's a strong demand for tools which accelerate development by 1 to 2 orders of magnitude. And you have to do this no longer with toys like what I showed you with Lego, or even kits as simple as what I'm showing you here. These have to be in real world use cases. It is at the intersection there that the real advancements will happen. So you all know, I'm sure, about the hourglass metaphor, where your foundational technologies, you have some kind of way to pull them together in an open platform. And what that results in are emergent technologies of a kind that never existed before. So if you look at the mobile and IoT world, Android and iOS play that role. If you have one of those platforms, you can run apps from the Google Play Store or the Apple App Store. It doesn't matter which device, as long as it has all the right sensors, you're insulated from the specific. So this is a very vibrant ecosystem. And of course, the mother of all ecosystems is the internet ecosystem, which was certainly enabled by the internet itself, and also by the web and the web browser. So I believe that there is a new world waiting to be created, which leverages many of the advances in deep neural network-based computer vision, in wearable devices, in edge computing, and 5G, and that world, rich new world, is going to be very exciting in the decade and more ahead. So I'd like to close with the following observation. Artificial intelligence is measured against real human intelligence. That's the standard of comparison. Now, evolution took 1 billion years to evolve us. We are successful. We are successful autonomous entities. And we succeed because the neural networks in our brains and our sensory systems have been exquisitely tuned for various applications that we use every day, fast and accurate. Now, we are trying to beat humans, to augment humans. We don't have 10 to the 9 years to wait. We barely have 10 years to wait. And so the only way to make progress at that level of acceleration is to somehow take advantage of approaches that evolution does not have access to. And so offloading computation over wireless to edge computing is such a capability. What it lets you do is to use compute while you're mobile in real time, using resources that are larger, heavier, more energy hungry, and more heat dissipative than you could ever carry or wear on your body. So very exciting. And I think the future is going to be quite interesting to watch in this space. Thank you very much, Indy. I'm done.
Thank you. Thank you so much, Satya. That was truly inspirational. We now have time for audience questions. Please send us your questions via the Q&A box rather than the chat box. Carrie Karaholius and I will alternately read the questions now. I'll start with the first question from the audience. First question comes from Vikram Madhve, who is a professor of computer science at the University of Illinois. He asks, the time breakdowns for your example applications seem to assume that the cloudlet is about as fast as the cloud. How could the applications and technical challenges change if edge compute happened on small devices like wearable devices or mobile robots?
Well, it depends on whether or not you use edge offload. If you say for whatever reason you cannot, then you have to accept one of two things. You have to accept slower responses, you have to expect less accurate responses, or you have to somehow come up with highly customized ASICs that are perfectly tuned to the application. Notice the point I made about human beings and evolution evolving us. We don't use edge offload up. Humans do it all in our brains. How does that work? It's no different from a mobile robot. The difference is the unique ASICs in our brain that are carefully tuned in application-specific ways for face recognition, for language recognition. The areas of the brain which have been developed specifically for these tasks. And in a recent Hot Mobile paper, I actually speculated on the relationship between edge offload and custom ASICs and what path they would take for the future. And so one way to think about this is using edge offload is a way to discover what ASICs should be built. And I think that is the path that is likely to succeed.
Okay, the second question comes from the CS department. You mentioned that the most profound innovations disappear as they're used. Today, we are finding that such seamless interfaces, disappearing interfaces, often obscure algorithmic curation manipulation that is sometimes biased. And there are calls to push back on seamless interfaces and to celebrate the seams. How do you see us creating ubiquitous computing systems given these disappearing technologies, and how might we be able to audit them given how fast they give information to understand some of this bias?
I think, sure. I think it's an excellent question. There's no question that when you rely on these hidden algorithms that work so fast and give an answer so fast, you may be unconsciously biasing because those algorithms have built-in biases that you're not aware of. I don't have a perfect answer for you, and I suspect that there is no answer. Humans are biased. We come with prejudices. That's why there are courses such as Bias Busters, which people have to teach, explicitly learn how to, how to overcome them. There's a wonderful book written by Daniel Kahneman, and I've forgotten the name of the book, but it talks about experts and how they build expertise that allows them to be fast. And basically the point is that the act of building that expertise includes certain biases that in fact that they will never be conscious of when they use that expertise. They think of, the title of the book I think is something like Thinking Fast, Fast, Slow, right? Whatever the title is. But I think this is a deep point, and I don't think we will get away from it. I think, you may have Microsoft's algorithms, which are biased a certain way, and Google's and Meta's and somebody else's, or your own, which may be biased in a different way. But I don't believe there will ever be a totally unbiased algorithm. Because if nothing else, the training data that is used to train the deep neural networks implicit in these algorithms may involve bias. How are you ever going to guarantee that that training data is not biased, especially in the light of future inputs? Which
I'm just going to add my own commentary on this question, which is I personally think we should consider how to audit these to mitigate certain directions if we know they're going in the wrong direction. But I want to leave the floor open to the students and the other faculty instead of jumping in. I'm sorry.
All right. Next question is from Joao Marcos Correia Marques, who is a PhD student in the CS department here. He asks about the flop of Google Glass. Why do you think it failed while being such a powerful enabler for augmenting cognition?
That's it's a good lesson in humility that is needed. As a piece of technology, I have to confess that the Google Glass is brilliant. It only weighs 36 grams. You can put it on your head, use it for many hours, and you hardly notice it's there. Other wearable devices, and the contrast is Microsoft HoloLens. I mean, that thing weighs over 400 grams. You put it on your head for an hour and you're aware of it. It is much fancier, much cleverer, but in the long run, it's a fair question to ask which is more important. So that's by way of technology. The answer to the question why it failed, frankly, I think it was hubris. The kind of use cases that I'm describing to you are very focused use cases where perhaps to help a repairman or to train a doctor or some task-specific way you're using these devices. And today, this is what Google is using them for. It is actually commercially selling these devices for industrial use cases. But the original introduction was positioning it as a consumer device that would help people access to all of the internet services, and also to be continuously having a video camera, looking at scenes, etc. And I think the pushback from the community, rightly, about privacy was huge. And I think it is an example of an overhyped and poorly thought out introduction that actually hurt the device. I think technically the device is excellent.
Okay, next question is by Elahe Sultanagai. She is faculty in the CS department at UIUC. It's a very inspiring talk, thank you. Perceiving the world is a big part of any cognitive assistance system. Right now, we assume a camera on AR headsets or glasses, but how do you envision the future of machine perception in these systems? Should we socially accept that everybody is going to have a third eye recording everything and potentially sharing it publicly, at least with edge compute nodes? Where do you see privacy in this vision?
So fair enough. First of all, there's no reason to persistently store what the video capture consists of, right? Because you only need to analyze it in real time to give responses. So I think that privacy concerns are less if the video is deleted within a few seconds of capture. You capture the video, you process it, you give feedback, and then you delete it. So it's transient. So as long as there's no record, persistent record of the interaction, I think the concerns are less. Second, it just pushes this one level further, which is how do you know that this cloudlet is not persistently recording that video? There, I think the point that you made about auditing or some process of certification, which says that indeed this hardware-software combination has been examined, has been found to obey the privacy constraints that the following code has recommended, and you give the stamp of approval, the good housekeeping seal, or the underwriter's seal of approval, or something like that. I think that's what's going to happen. That it's very important to appreciate that privacy is especially a concern because data can be stored for long periods of time. It's a question of using and throwing away. Many concerns become less. They don't vanish, I don't claim that, but they become less.
Right. So we have a lot of questions built up. I'm going to ask one last question because we're running out of time, and then we'll communicate the rest of the questions that we couldn't ask to Satya so that he has all the questions. So the last question actually was asked by two different people, Julia Hockenmeyer, professor of computer science, and Yana Zhao, grad student in chemistry. I'm going to combine their questions because it's about the same thing. How does the IKEA assembly system that you presented know what errors are possible at which stage? Can the system generalize to new types of furniture, or does it need to be programmed specifically for each item? Are the mistakes previously presented to, and are the mistakes encoded in the system?
All good questions. So let me answer them in reverse order. At the moment, the apps have to be built by hand for each specific task. There's no generalization of the task that is possible at the moment, right? So future tools that generalize would in fact be very attractive if you could make them do that. Second question, how do you know which is correct and which are not? So the way we think of this is you are building a state machine. What you are constructing initially is a state machine that sequences you through a correct execution of the task. That's the first thing that you build. And we have tools that help you do it. And once you've built that, now you have a system that, as long as you don't make mistakes, will guide you correctly. It is at this point that things start getting interesting. How do you add the error states that are important? The question is, how do you know what kind of mistakes the person might make? You can combinatorially write out all the possible transitions that would be bad, but that's a huge exponential, and most of those states will never be reached. So we think what might be a practically a good way to handle this would in fact be to use the human escalation, where let's say on day one, the app is released, can handle correct sequences, but nothing that's an error. The first time some user makes an error, the system is in a state that it doesn't recognize. It hangs, the user gets tired, and he presses the button that says call expert. Well, the expert now is on a Zoom session, obviously sees what's wrong, guides him or her on the right path, but the Zoom session can record the error, just like this session is being recorded. Over a period of, say, weeks, as more users use this app, you can build up basically a repertoire of common errors that people seem to be making. And then from there, either by human inspection, or if you can use machine learning and extract this knowledge, you identify common errors and then augment the state machine to recognize those situations. So you will have almost a DevOps model in which the app improves over time as people use it, and the commonest errors will be handled more and more automatically because the software gets more sophisticated. But there's always the escape hatch to the remote expert. I think that's a development methodology that has some chance of actually being successful and resulting in a economically successful approach to building these kinds of systems.
Thank you, Satya. Thank you for that wonderful talk. Very insightful and timely. This was an awesome season finale for our fall 2021 speaker series. Thank you all for joining us today. A recording of this talk will be posted to our website, just-infras.illinois.edu, and ASL interpretation will be available with the video. You can find all our past talks at that website as well. We will be back for more public-facing events. We hope to see you in future events and engagements of the Just Infrastructures Center. If you'd like to send us feedback on our talks and our series, you can contact us at the email and Twitter handle that has been posted in the chat. I'd like to take a moment here to thank our production team and invite them to re-video at this point. None of this would be possible without the back-end work of Mitchell Oliver, Jingi Gu, Silas Su, Tiffany Lee, Gabe Malo, Jorge Rojas, Vinay Koshi, and Sam Walco. A huge thanks to the UIUC's Dress Office and the ASL interpreters who have helped us throughout the speaker series this year. We'd also like to thank Rachel Switsky and the Siebel Center for Design, the iSchool, and the CS department for accommodating our live broadcasts in their physical spaces. Thank you, everyone, and thank you all for joining us. We will be back.
Bye.